I'm assuming from previous classes that you have done something along the lines of, I need to be able to take an idea and turn it into a data sciencey sort of project. By which I mean, you already know that you need a training set, that you need to split off a validation set, you need to split off a test set, that you need to train a model, evaluate the model, maybe retrain the model on your full data, so that you've got a thing to deploy. That's kind of table stakes. Of course, that's a thing that has to happen. There's a whole bunch of other, of course this has to happen. You have to think about bias and ethics and whether it's legal to deploy this thing, all those sorts of stuff. I'm not going to talk about that. What I'm going to talk about specifically is within the field of NLP, right now, today, what are the design principles to keep in mind for what you want to think about when you're designing an application. And my kids actually did have time to determine whether this was the appropriate meme or not. When I was preparing this lecture, I sort of reached out to a few different people and said, look, do you think this is a fair statement of what the design principles should be? So there's 9 design principles I'll talk about. And what was interesting is how incredibly contentious it got. So I'll try to give both sides of the argument, but I'll keep in mind that I'm extremely biased, so I have, what I think is the case. What I did find is the majority of people agree on the majority of these design principles. So where people disagree, they'll go, no, that's totally wrong. Meanwhile, everybody else in the room is like, yeah, that's totally right. So basically, it turns into a big shouting at cat kind of meme situation. Okay, first principle is design with the bitter lesson in mind. So Richard Sutton wrote this very, very short little essay, not even big enough to be a letter in a journal kind of thing. And he says the bitter lesson is this, that we've been trying to do AI since the 1950s. Fun story there is one of the very earliest AI researchers set computer vision as a summer project for one of the undergraduate students. So it's a bit equivalent to like Comp 8851. Could you figure out how to do computer vision so that computers can see and interact with the world around them? This is in a day when they had to use cameras that didn't even have CCDs on them. So 70 years, and in that 70 years, what we've found is that if you think really hard about your problem and you try to get to the foundational principles, and your neighbour just throws more compute at it, your neighbour wins. So we had speech recognition, which went from we're going to carefully break down the sounds and try to find which phonemes there are and where the vowels are, and we're going to do speech recognition, so speech generation by modelling human throats. And punchline is, in 2022 when the Whisper models came out, did it come from? People just trained massively big deep learning models on vast amounts of human speech that was transcribed, i.e. most of YouTube. And so that's incidentally why Whisper can happily listen to Chinese and transcribe English, because all of these Chinese language videos with English transcriptions, likewise French, German, Dutch and so on. Chess, the early computer chess games, all tried to calculate the value of a position. What happened in the end? Just brute force. The things that we seem to scale arbitrarily are search and machine learning. The bit of lesson basically says, throw more data at it, throw more compute at it. We are in an era where you can, so do. And he goes on a bit further and he describes it like this. There's this temptation all along to build knowledge into whatever agent that is doing this artificially intelligent thing. And it always helps in the short term. And it's really satisfying because you feel as though you've done something worthwhile because you've improved your model, you've feature engineered something, and in the end it kind of plateaus and actually starts stopping further progress. And you start discovering that other people who didn't try to make their agents smarter, but just went with brute force and more compute power, tend to get ahead. And this is why it's known as the bitter lesson, because eventually you find yourself, after investing all this time and effort in feature engineering, extra capabilities, or thinking more about what the agent needs to do and putting your own intelligence into it, the bitter lesson is it doesn't help. It doesn't help over the long term, it only helps over the short term. And suitable memes. On the left-hand side, I'm not sure in this meme actually what the character's name on the left-hand side is, but it's pretty much all the things that we have thought were necessary and important in order to pass the Turing test were things like, well, we need to have semantic grounding, which I'll talk about later, and you can't just have pattern matching like the 1960s ELIZA. It needs to be grounded with intent, and you need to have framing and so on through a zillion things down here. Over on the right-hand side is, I'm just going to buy another couple of big GPUs and see what happens. And we've seen that process play out very rapidly over the last 12 months. If I wind the clock back to, where are we, March 2023, I think GPT 3.5 was still state-of-the-art. GPT 4 only came out was it end of March, I think? So the biggest context length we had was 4096 tokens or something really tiny like that. And we needed to have a whole bunch of extra capabilities to try and understand what the output from GPT 3.5 was. So we have these wonderful platforms for taking the output from an LLM and trying to check that it's right and check that it's in a bunch of different classes, which within a year were obsoleted because now we do function calling, we do agentic behaviour, we do GPT-4 made a lot of these things irrelevant. We've learned a whole bunch of tricks since then. That is literally only a year ago. Fixing some limitation that you encounter with an LLM, by the time you've actually fixed it, the next generation of LLMs will already have obsoleted the entire piece of work. So that's the bitter lesson. There are some objections to it. Of all the 9 principles I'm going to talk about, this is the one that gets the most arguments. All of the examples that Richard Sutton used, so speech recognition, chess, Go, translation and so on, they actually required major leaps forward in how search and learning worked. The reason that the GPT models worked is because we had a new way of doing machine learning, which was transformers. Transformers are like being able to take the derivative of a dictionary lookup and yippee-yay, if you can do that, suddenly a huge range of programs are possible that weren't before. The scale up of Go came down to we got very fast at doing parallel searches. The other objection that people raise is, well, it's very nice to know that in 2 or 3 years' time, my current work is going to be completely obsolete. That's actually utterly depressing and miserable, but I still need to deploy something today. So, great, I know that I shouldn't try very hard, but I've got to tweak this model, I've got to put in additional information into it to make it smarter, because I've got to get paid this week, not sit back, twiddle my thumbs, and in 3 years' time, just have it happen out of thin air.